Hey everybody, let's talk about kinetic energy for objects that are rotating. So let's consider, let's say for now, some kind of massless disk, and then let's say we attach 3 different point masses to this disk, and then the entire thing rotates counterclockwise, say this way. So then this is the rotational axis, and here's some mass 1, mass 2, mass 3 at some radius r1, this is at radius r2, r3, right? So then mass 1 will be traveling like this, mass 2 will be traveling like this, tangent to the path, mass 3 like this, tangent to the path. This is some angular velocity, omega. Okay, so what's the kinetic energy? Kinetic energy. We just add up the kinetic energy for each of the 3. Right, so let me just write it like this. 1/2 mv squared. Right, so in this example, I equals 1, 2, 3. Okay, now remember, what's the relationship between linear velocity and angular velocity? Is like this. So this linear velocity we can replace with r omega, and then that squared, right? So r squared omega squared. Okay, and then if these masses don't move with respect to each other, so imagine this disk is rigid. You can't deform the shape. Then imagine 2 people lying down on like a merry-go-round. And then we rotate it 90 degrees counterclockwise. Who goes farther? Right, the person on the left here goes this far. The person on the right goes this far. So definitely this person moved farther, an arc length. And let's say this takes 1 second to rotate. Then definitely this person is going faster because it's a longer distance in the same amount of time. And then similarly, the acceleration would be more because this person accelerated to a higher speed in the same amount of time. However, by what angular displacement did they move? They both rotated 90 degrees, right? Like pi over 2 radians. So they have the exact same angular displacement. And if it takes, say, 1 second, then it's the same angular displacement and the same time, so they have the same exact angular velocity. And if they got to that same angular velocity in the same time, they have the same angular acceleration. That's assuming they don't move with respect to each other. They just stay there. So for a rigid body, where these masses don't move with respect to each other, so there's no deformation of the shape, this angular velocity is the same for every object. So we can take that out of the sum. We could have pulled that half out of the sum as well. Omega. So this is the same. I can take it out of the sum. And let's say we consider like every single molecule in this disk. So, or let's say n of them, like n masses, like this, for n objects. This quantity is called the moment of inertia. So we just call that letter I. So let me rewrite this. Kinetic energy is 1/2 I omega squared. This is kinetic energy for an object that's rotating. So this is rotational kinetic energy. And the moment of inertia is mr squared. that's if you have n discrete masses. We can kind of calculus this thing. So instead of point masses, imagine an infinitesimally small discrete mass, dm. And then you find the position squared of each of those differential masses, and then you integrate that. Right, so this is basically the calculus version of this. So for this semester, we'll never discuss objects that we don't already have an entry in a table like this. So we'll only ever have objects that are like a hoop or a cylinder or a slender bar or a ball. And for other shapes, we'll leave that for future semesters. Okay, so let's do a quick example. Let's say you have like a pulley like this. It's a disc. And then there's a block over here and a block over here. And let's say this is smooth. And let's say you release this from rest and block 2 drops to over here, some distance d. So block 1 goes over here, some distance d. So let's start at rest, release it. All right, block 1 goes toward the left, block 2 drops down. The disk will rotate. And let's say the disk is a mass md for the disk and radius r. This is for the disk, our pulley. Okay, let's try energy conservation here. So there's no friction, so there's no work being done by friction. Work by friction in this example is 0. So energy is conserved. So how much energy initially? Okay, so for gravitational potential energy, depends on the datum. So for block 1, let's say the datum is here. So the potential energy is 0. For the disk, let's say the datum is here. So potential energy is 0. For block 2, how about I put the datum here? Okay, so it has gravitational potential energy, m2g d. Okay, and then this is at rest. Kinetic energy 0. That's at rest. The pulley is at rest, so no kinetic energy. Okay, so final. For block 1, the datum was here, still at the datum. Block 2, the datum is here, so it's at the datum. For the pulley, the datum was here, it's still there. Okay, so we're done with gravitational potential energy. Block 1 was at rest, now it's moving some speed v, so it has kinetic energy. Block 2 was at rest, now it's going some speed v, so it has kinetic energy. The disk was at rest, now it's rotating with some angular velocity. So it has kinetic energy, how much? 1/2 I omega squared. Okay, what is I? We just look over here, so it's a disk. So you see right here, disk. So this one right here, 1/2 mr squared. So for the pulley, this is 1/2 mr squared. And we know the mass of the disk and we know the radius. Okay. So then let's say if we're given both masses, so if we're given, say, both blocks, the mass of the disk, that distance d, and the radius, what's left unknown? Let's say we want to solve for the speed. So we don't know this, we don't know this, we don't know this. There are actually 2 unknowns, but we only have one equation. But then what's the relationship between V and omega? So if we assume this disk is rotating and this string over here doesn't slip, then the relationship between the speed here, right? So this is, let's say, the string here, right? The string is moving this way with some speed v, because the block here is moving with some speed v, the block here. What's the relationship between this speed and this angular velocity? Like this. Right, that looks familiar? So here we go. We have two equations, two unknowns. Okay, so that's rotational kinetic energy. Let me get more into this and explain more about the moment of inertia in the next video. So I'll see you on that one.